Good morning, good evening, good afternoon. In today's video, we'll discuss about black holes, but we'll learn about it more deeply. We often associate black holes with singularity, and this is a singularity, where this is the space-time graph, and this is bent by some gravity to an infinitely dense point, and it just goes out of the plane. A black hole, in simple terms, is this: the singularity and the empty space around it where light cannot exit, so we cannot really see anything. First, let us take the example of our Earth. This is the Earth's atmosphere, and let this be the outer layer of the atmosphere. Let us take a hypothetical case. If an alien species decide to invade us, then it will enter into our atmosphere. Let's say it enters this bit. Then they realized that they cancelled this plan. Now let's say the rocket is here. Then it would need a speed of 11.1 kilometer per second to escape the Earth's gravitation, and this speed is what we call the escape velocity of any object. So let's suppose this atmosphere uh, let's suppose this atmosphere layer, the outermost layer, is R. So once a particle or a light gets this close, maybe it can escape the black hole by just speeding enough. Like, if its speed is enough, it can just move away. It's quite possible. And here it would be hard, but it will be possible. It still would be possible. And at this point, spaghettification process will already start. Now suppose a particle crosses this line, I mean this boundary, then it would need a velocity greater than light speed, and this is not at all possible in standard physics. If it is a light particle, then too it would be impossible for it to escape after this boundary, and this is what we call as an event horizon. Yeah, movies often show black holes as really large, but have you ever wondered how scientists calculate their mass? We have two ways, two general ways. The first method we have is the Keplerian method. The mass of a black hole, say capital N, is equal to small r. This small r represents the radius of the black hole, multiplied by v square. Here v is the velocity of an object orbiting around the black hole, divided by capital G, universal gravitation constant. Now this method has its limitation, because what if we don't know the orbital velocity of any object? This method can only be used when orbital velocity is provided. Otherwise, we use another method, Schwarzschild radius formula. About this state, m is equal to r s c square divided by 2g. Here r s is Schwarzschild radius and the radius of event horizon. C is the speed of light in vacuum, and g is the universal gravitation constant. Both of these methods, when used, give us the mass in kilograms.